Okay, today on the bench, honestly, it doesn't really matter what specific radio it is. I just want to demonstrate why it's important to let a radio warm up. Well, actually, not just your radio, even your test equipment. Now, what this is it's a realistic TRC 449. So it's a UPD 858 AM sideband radio chassis. Now, if you're doing alignments, because I have seen this happen before. Somebody does an alignment, and they say they're and someone else, whoever it was done for, they'll say, well, the frequency's off. And you can check the radio, and the internal test points inside the radio where you're at when you're actually doing the alignment on a radio, if you check at those test points when the radio's cold, the alignment's perfect. So whoever did the alignment, what they did is they got done doing any work they had to do to the radio, turned it on, hooked up their frequency counter, adjusted the frequencies. The problem is the PLL alignment, when you do a transceiver alignment on a radio, in most radios, CB especially, the first thing you do in an alignment is the frequency adjustments. And the problem is those will change over time as the radio warms up. And I want to show that. So, and it's also not just the radios, it's also your test equipment. Everything that has anything to do with frequency has a crystal. And those crystals, the frequencies that they oscillate at change as the temperature changes. Now, some are better than others. Some, once they warm up, are extremely stable. Now, it's something you'll never see in something like a CB radio, but test equipment, and even high-end radios, you can a lot of times get high-stability oscillators for them. You can get OCXO, TCXOs. You can get, the oscillator, the actual little crystals down in the radio. Well, they won't just be little crystals. They'll be in their own little oven-controlled box. But, so it's important not just that your radios have had time to warm up, but that your test equipment has had time to warm up as well. Now, I have switched over myself. I use a GPS DO, it's a GPS disciplined oscillator. So basically I have a frequency standard here that all of my test equipment runs through. So that generates a 10 megahertz output signal, and that is compared to the reference, basically the reference from the GPS satellites. So I know that I have an extremely high precision frequency to use as a reference. And then I have that run through a distribution amplifier, because most test equipment, like my communications test set, spectrum analyzers, frequency counters, signal generators, all of that stuff has a 10 megahertz input on the back of it, where I can run a reference into. So I have my GPS DO reference oscillator runs into a distribution amplifier, and then all of my test equipment is attached to that reference oscillator. So everything is running using the exact same oscillator reference. The other thing is, that's the one piece of equipment that I have that never gets shut off. All of this stuff, when I'm not using it, as soon as I'm done with it, I turn it off. The nice thing about if you leave your oscillator on, the longer it's on and the more stable that reference oscillator becomes, the more accurate it's going to be and the more stable it's going to be. But in any case, I want to actually show the radio. So here's a good example. UPD 858 chassis, they're extremely popular, probably the best AM sideband chassis ever made in the mid-market. I say mid-market. It's not the best AM sideband radio ever made, period. But when it comes to reasonably priced AM sideband CV radios, it probably is the best. I know a lot of people argue, they love their Cobra 148s and Cobra 2000s. Don't get me wrong, those are great radios too, but these are even better. It just cost a hell of a lot more to make this radio than it did the 148s. I don't want to say it was no expense spared, but they are really good radios. But even these really good radios the frequencies drift as the radio warms up. Now, once they warm up, they're fine. Even the 148s, the 2000s, the Cybernet chassis, all of them. Once they warm up, they're stable. They're fine. They're not like a lot of your modern radios from Ranger or Galaxy. Well, actually, they're all made by RCI Ranger. That's who makes most of the boards and almost all those radios. Those things are horrible. Oh my God, they just drift all over the place. These, once they've warmed up for a short period of time, they're very stable. But I want to show that frequency drift. So this radio has not been on today yet. It's off, other than I just turned it on for a quick second to kind of get my spectrum analyzer zeroed in. But what we're going to look at it with, now I could hook it up to a frequency counter, but you're just looking at numbers bouncing around. So for a little bit better graphical display, we're going to be using the spectrum analyzer. Now most people are probably familiar with spectrum analyzers. You'll run those through an attenuator, and then you can hook them, directly, to the output of the radio. But you can also use those inside of a radio. So that's what I have here. I just have an oscilloscope probe hooked up through a DC block. You want to make sure you don't run DC voltages into your spectrum analyzer unless you want to let the smoke out of it. So I have a really high quality DC block right there. But that's all it is, just the spectrum analyzer, DC block that stops DC voltages from getting into the spectrum analyzer, and then it's just attached to TP8 in the radio. So we're checking there's the tripler oscillator circuit. So there's actually 3 crystals. We're just going to be looking at the one for AM. All 3 of them are going to do the same thing, whether it's the upper, lower sideband or the AM tripler crystal. They're all going to drift about the same amount because they're all just right there and located in the same area. So I'm going to turn the radio on. I have the spectrum analyzer set for a 1 kilohertz or 1000 hertz span. I have the center frequency set to 34.985 megahertz on channel 19. So when you're doing a transceiver alignment on one of these, you attach your frequency counter, or in this case, we're using the spectrum analyzer as a frequency counter, but that's attached to TP8, and then you select which mode you're going to adjust, either the AM, the upper, or the lower sideband oscillator, and you adjust the trimmer capacitor in there to get that frequency dead nuts on center. Either in the case of AM, 34.985, or for upper or lower sideband, it would be 34.975 or 34.925. Because that takes into account the offsets for upper and lower sideband. So we turn it on. I'm really quickly, because the clarifier does play a role in that, because the clarifier is part of that circuit. I want to really quickly, as soon as I turn it on, I'm going to dead center the clarifier. So the marker, I have a continuous marker on, so it's going to track the frequency. Doesn't matter where it's at, but I want to put that dead center in the screen, and then I'm going to basically stop the camera, and we'll come back and look at it. So turn the radio on, and you can see as I turn the clarifier, you can see the signal moving left to right there. So I want to get that as close to center as I can. So right there, 34.985. And the marker right there, that's actually reading out the frequency. But we're at 34.985. And just in the time I've turned it on, it's already drifted down some. It's already down to 34.993. So it's 34,984,988.91. It's jumping around right now. But you're going to see this radio change probably, if I had to take a rough guess, let's see, that's after, let me just figure in my head here, because that is a tripled frequency. So that's another thing to remember. That frequency that's being generated right there is not the actual crystal frequency. That frequency is actually tripled. There's a circuit in here called a tripler circuit. So you have the oscillator, the output of that oscillator circuit runs through a tripler, which does just what it says. The frequency is tripled, which is what is being displayed right there. That's where TP8 is located, the test point 8. It's located after the tripler. So any error, and that's another thing, any error in the crystal frequency, or in the oscillator circuit of that crystal, the error is tripled. So for every 1 hertz of error in the crystal oscillator, you'll end up with 3 hertz of error there. 10 hertz of error at the crystal, 30 hertz of error, out here at the output. And you can see we're already at 34.984966. So we've already dropped a considerable amount already. So what I'm going to do is I'm going to pause the video, and then we'll come back in like 10-15 minutes. I'll just keep an eye on it, and when I see that it's finally dropped down to the point where it's not moving anymore, I'll come back. But you can see that little, move the camera up here slightly. You see that little white dot at the top there? That's the marker. And when we first started out, we were dead center on that line right there. That is the center. You can see it's already shifted over. So each one of these vertical lines here represents 100 hertz, because there's 10 divisions, and we have the span set to 1000 hertz. So you can see it's already shifted, actually more than 50 hertz already down. The frequency has dropped down that much already. So that's why it's extremely important to let your radio warm up. Better yet is to put the cover on it. Personally, that's what I'll do. I'm just doing this, so you have to remember, this is open air right now. So heat that's being generated in here is escaping. Now the board is warming up and the components will warm up. But if you put the cover on this radio, it's going to warm up even more. And you're going to have more frequency error. So ideally what you should do if you're going to actually be doing alignments yourself, turn the radio on with the cover on. You don't need to screw it on. In matter of fact, you don't even, in a case of like a radio like this, a mobile radio, you don't even need to put both covers on. The bottom of the radio is setting flat on a workbench, so it's not like it's getting really any air circulation anyhow. Just put the cover on this side of the radio, the part that's exposed to the atmosphere basically, turn the radio on, let it on for 15 or 20 minutes. Do something else in the meantime. If you've done a bunch of work to this, you've probably got a mess, like right here. I've got a bunch of drawers of capacitors to put away, because I just got done replacing all the electrolytic capacitors in this. And yes, that is a PLL chip there that was replaced in this thing. Someone had done a channel modification, and yeah, they've got pins bent. There's pins that are broken off and had been bodge soldered back on. So, I need to clean my bench up. That's a good time to do it. You've done your repairs. You've verified everything works. You're ready for the alignment. Turn it on, plop the cover back on it temporarily, just set it on there, and while it's warming up, you can be getting out your service manual, you can be setting up your test equipment, especially if you're not running a reference oscillator that's on all the time, you're going to want to turn your test equipment on, your frequency counter, and let it warm, not only the radio warm up, but you're going to want to let your frequency counter warm up as well. Put all your parts away, clean your bench up in the meantime. You have to use your time wisely. But so we can already see, just in the time I've been turned it on and talking, we're down almost 100 hertz already. So let me stop the video, and I'm going to do just that, clean up my workbench, and we'll be back to see exactly how far off the frequency drifts on this radio. Okay, so it's been probably somewhere around 20 minutes now. Like I said, use that time to do something. So cleaned off the bench and whatnot. But we can see the frequency that started off, I've got to look through the viewfinder here, right here, has now shifted over to here. So it's shifted, well, exactly, bouncing around a little bit, but almost exactly 200 hertz. That frequency has shifted down. We started out at 34.985. And the marker is now setting at 34.9848. Actually down a little bit more. So it's still shifting, still warming up a little bit. But like I said, that would actually occur a lot faster if I had put the cover on top of this radio, the warm up. And that's why I suggest doing that. Put the cover on the radio, turn it on, have everything ready, pop the cover off, and then quickly do your alignment. Because as soon as you take the cover off, the parts are going to start to cool down and the frequency is going to be moving around. So like I say, you want to take your time doing it, but try to get that part of an alignment done as fast as you can. Take the cover off, have your equipment, all your alignment, any tools you're going to need to adjust, so ceramic screwdrivers or whatever you're using for adjustments. Have all those out already. Pop the cover off, connect your frequency counter, and do the calibration. But like I said, I just wanted to show that because, now, like I say, this is being tested after a tripler circuit. So if we have, actually it's down even another almost 10 hertz there, so like 210. But let's say 200 hertz. That's a tripled frequency. So a lot of people say, "Oh my God, this thing has drifted 200 hertz." No, you have to remember it's tripled. So 200 divided by 3 is 66.666. So say 66 hertz. So the actual frequency has only changed 66 hertz. And then, but like I say, that error is then tripled. So you go from 66 to 200, or now almost 210 hertz. Like I say, this time it would happen a lot faster if I'd put the cover on the radio. But I just wanted to let everything set just as it was. So it's just something to keep in mind. When you're working on anything that has oscillators that needs to be calibrated, temperature. I think Sam's. I don't want to go telling a fib here, so I got to actually look at the book. Can't remember if they tell you to let it warm up or not. They usually do. Yep, I was gonna say it's one of those blocks I never read anymore. I just know better. But yes, allow 15-minute warm-up period right there. And I think a lot of people miss that step. Allow a 15-minute warm-up period. So, extremely important. And this clearly demonstrates why that 15-minute warm-up time is extremely important. Like I say, put the cover on it. It'll warm up faster and it'll stabilize a lot faster. But so that way when you do an alignment, you're doing a better job. Because if I had this radio turned off, it was at ambient room temperature, hooked up a frequency counter to it, and done the alignment, by the time I got done doing the alignment, if I reattached my probes in the PLL synthesizer circuit, at TP8, and there's multiple test points in here, because there's multiple frequency adjustments. There's more than just these 3 crystals. There's another 2 over here. But by the time I got done the entire alignment procedure, if I came back in and rechecked those frequencies, that's what I would have seen. I would have seen, what the hell, I just aligned it, 15, 20 minutes ago. How in the hell is it off already? Well, it's not that it's off already. The problem is you never let the radio warm up like the service manual says. So, and the problem there is you align the radio. Now, granted, the radio has a clarifier. If the radio is unmodified, the clarifier only affects the receive circuit. It does not affect the transmit circuit. The transmit frequency adjustment is on the inside of the radio and should only be adjusted by a technician working on a radio with proper equipment. Now, if a clarifier is unlocked, where the receive and transmit frequencies are locked together, then yes, that's, when you turn the clarifier, that's going to change both receive and transmit frequencies. But yeah, it becomes an even more complicated problem if the receive and the transmit frequencies are 2 different frequencies. So just because that's more components in circuit that can vary. So the point being though is you turn the radio, you center the clarifier. You turn the radio on, you do your alignment. You send the radio back to the customer. The customer turns the radio on, it warms up, they use the radio, and then they contact you and say, "But my clarifier's not centered." And you're like, "Well, what do you mean it's not centered? It was centered when I did the alignment." But yes, you didn't allow the radio to warm up. So as the radio warmed up, you then have to turn the clarifier more to bring it back in. So actually, let's just see how much. Let's see here. I need something, because it's going to be hard to see chrome knob, how much I actually rotate the knob on this. So let me grab a piece of Post-it tape. Love this stuff. And the people that make Post-it notes, they also make little rolls of it now. It's just the sticky part. So I'm just going to stick a small piece of this on this knob so we can actually see how much this clarifier would change. I'll try and get this centered. So let's say right about there. Now, what we're going to do is we're now going to turn the clarifier until we bring that peak back dead center, which would be in alignment. See how far that's moved? That clarifier that started out perfectly centered is now off by what? Like probably more than 1/8 of a turn. You know, that's probably more than 1/8 of, 1/8 of a turn maybe. Maybe not that much, but still, it's approaching 1/8 of a turn. So, you know, but that's something to keep in mind. That's why your customers might be contacting you and saying, I just had an alignment done, my clarifier's not centered. Well, that's because as the radio warmed up, it shifted. Because I think some people don't realize that the clarifier is part of those circuits inside of a radio. So, like I said, I just don't want to make this an extremely long video. I just wanted to demonstrate that to actually show the importance of letting your radio warm up, and the same thing with your test equipment. If you're not using something that stays on all the time, that has a very stable frequency, you're going to want to turn your test equipment on and let it warm up too, because it's going to do the same thing. The frequency is going to change as it warms up. So there you go. I hope that helps, and might explain to some of you why, from the time you turn your radio on to the time, you know, say 15 minutes later, why you have to tune your clarifier. And then once it's warmed up, you never really seem to have to touch it again. That's why. As the radio warms up, the crystals, and it's not just crystals, there can be coils, capacitors, trimmer capacitors, all kinds of components in here. As they change temperature, because they have a tolerance, you know, plus or minus whatever, and that can change as the temperature changes, the values, the capacitance, you know, it can change a couple picofarad in either direction, or the inductance, you know, might change a few microhenries, which throws the oscillator circuit off. So it's just something to keep in mind. So I hope that helps explain that a little bit, and the importance of warm-up times.